So the title of my presentation is End-of-Life Indices to manage the manufacturing phase during the product design process. Through my presentation, I will talk about the research context, little background, the methodology used, EOL indices defined, and conclusion and future works. So, which are some of the main environmental problems in our society? The increase of wastes and the increase of raw material consumption. How can we try to solve these problems, these issues? We could develop sustainable products and services, which means the implementation of an eco-design approach and the introduction of environmental requirements as design drivers. This brings us to develop methods and tools to help product designer in the manufacturing process, definition and planning, where the manufacturing can be defined as the reduction of a product into its individual components with the aim to reuse or remanufacture the parts and to recycle the materials if the two first possibilities are not applicable. So, new challenge for industrial companies is to achieve a profitable business market based on product retirement with the reintroduction of parts in the end of life products as a second life. So, practically means make a business out of waste. During the last year, from the traditional design, we shift to the eco-design, which involve the raw material extraction and processing at the beginning and the end-of-life stage at the end. And today, in this presentation, we focus on the end-of-life. So, the final aim is to create a closed loop, and so we add to the blue steps, we have the green ones that are recycling, remanufacturing, and reuse. Actually, the 3R concept is not only increased, but is evolving in a 6R concept and approach. In fact, we add the reduce, recover, and refurbishment. In this graph here, we can see that if we increase the disassembly range, the recycling of course increase, but also cost due to the actions and processes increase. So we have to find a certain range that allow us to obtain the highest benefit, and so-called optimal point or optimal strategy. So, which are the main problems we have to face? Research study focused mainly on product sequence, and we found a lack on end-of-life methodology, but especially we found a lack of information for the designer in order to include end-of-life strategies within the design process. And also lack of indices that can give quantitative feedback, not just guidelines or suggestions. So we need the development of an end-of-life approach that can be applied during the early stage of the design, and development of 5 end-of-life indices based on environmental and economic aspects. It's well known that although 7% of the entire product cost is related to the early design, decision made at this stage affect the 80% of the total product cost, so they are quite important, and if a product can be said to be sustainable is determined by the early stage of design. And also managing the EOL strategies can reduce the cost and the environmental impact. So through the evaluation of such indices, the designer is guided to the product redesign with improving its sustainability and favoring closed-loop strategies. Of course, the advantages of this methodology are more visible where the product is quite complex. So here we can see the product design phase. We start with a bill of material, and then we calculate end-of-life indices through some parameters that are based on both economical and environmental constraints. And then we define end-of-life best scenario. And then we, as I said, we aim to create a closed loop scenario. And we give to the designer a quantitative feedback, such as numbers, for instance. Here there's a list of parameters presented inside the formula. So we have some cost, like a cost of disassembled parts or a cost of deterioration due to the use, cost of the part to be replaced, and some unitary cost like economic value of recycled material, the energy for virgin material, minus the energy for recycling treatment. Here we have some other parameters that will be used in the indices calculation. The material eating value, the cost of refurbishment, production of virgin material, energy cost. And here are shown the 5 indices. As you can see, there are 5 scenarios: reuse, recycle, remanufacture, incineration, and landfill. So now we try to have a look a little more in detail. For instance, the reuse one. There are 4 possible results and 3 range. If we have a positive result, means that reuse is suitable and economically beneficial. If we have a negative result, that means that reuse is not suitable. And if we are like between 0 and +1, it means that it's suitable, but there's economic benefit only if the production of a new component is higher than regeneration cost of the component. And here is the recycle. Again, 4 results and 3 ranges. Always the positive value means that it's suitable, the negative means that it's not suitable. In this case, if we are in the middle, recycling is suitable only if the recycle cost is lower than the manufacturing cost. Here is the manufacturing index. In this case, again, I will just explain the middle results because the other 2 are the same as before. And manufacturing is economically suitable only if regeneration cost is lower than the reuse, the benefit due to the reuse of the product. Because when we remanufacture something, we have to take into account that we will have some expenses. Instead of the case we reuse, we do not spend any money for it. But if we are manufacturing, then we will spend some money, so the benefit will be lower. And incineration is environmentally suitable, but is economically suitable only if the profits given by incineration are higher than the cost of a new product. The landfill has only 2 cases, and it can be either suitable or not suitable, and it's the only index that has no 4 results. but it can either goes to 0 or minus infinity. So these indices may need a little interpretation, and to summarize, reuse is the best choice, followed by remanufacturing, recycling, incineration, and landfill, and not all the end-of-life scenarios are always possible, for instance with composite materials, and if indices are spread in the three ranges, then the most positive should be chosen, while if they are spread in the same range, then additional consideration should be done. And yeah, here we detail a little results. For instance, in the first range, we have like only 4 indices because landfill can never be positive, and if the material has a higher heating value, or combustion is powerful, or if energy is quite expensive, then incineration is the best option, of course. While reuse and remanufacturing are both optimal choice. However, as the designer has to take into account technical and functional requirements. And then remanufacturing, as I said, gives a lower economic benefit, and reuse is preferable than recycling, but recycling is preferable than remanufacturing whenever there's a high income. Whenever we make, let's say, a business out of recycling. And the second range, the designer must not, in the case reuse versus remanufacturing, the designer must consider not only the index value but also the benefit related to the economic savings associated with the absence of purchasing a new component. While in the third range, if the results is very negative, then the designer should revise the project. Recycle and incineration are not suitable, but they minimize the waste produced, and as I said before, reuse do not bring added value, however, can be cheaper than incineration and recycling because there are no additional costs. In conclusion, we developed 5 new indices, and we developed also a methodology to implement those indices, and we test the methodology and the indices with a cooker hood. And the study of end-of-life indices for components belongs to the WEEE category. And we also developed a tool which is to implement the proposed approach, which is the G.EN.ESI. And we also are working on the normalization of the end-of-life indices. Again, these activities within the G.EN.ESI project.